Hi friends, our next chapter is dual nature of radiation. In this chapter, we are going to learn more about radiation, but these are going to be different aspects. You are going to see a new nature of radiation itself. Let's get started. First of all, there is something called as electron emission. Metal contains many free electrons, right, which are in turn responsible for the conductivity. And these electrons are held inside the metal surface by attractive force of ions. So that's why they are held inside it. They can't just come out like that. I can bring them out if I produce or if I give some energy which is required to break those forces. That minimum amount of energy required to pull out an electron from the metal surface is known as work function, and it is denoted by this psi naught. Now this work function depends on metal properties as well as the nature of surface also. Okay, I have to give energy to pull out an electron. That is known as electron emission, right? How can I give that energy? There are many ways. One is thermionic emission. When you heat it sufficiently, the thermal energy can be imparted to the electron inside it, and hence it can break those attractive forces inside this wire, and you get electron emission here. This is one way. Other way is field emission. What you'll do here, you apply a very strong electric field such that the electrostatic force that acts on electron is enough to break the forces inside the metal, and hence you get electron that is pulled out of the metal. But the problem is here the electric field you have to apply, that is very high. It should be somewhere of the order 10 power 8 volt per meter. This is very high, right? So the other way of electron emission is photoelectric emission. This is important. We are going to get into details in this chapter about this emission. What is it? When you throw some light, when light of suitable frequency illuminates a metal surface, then electrons are emitted from that metal surface. This light generated or photo generated electrons are called as photoelectrons. This emission of electrons, this process is known as photoelectric effect. Now, after gaining sufficient energy from the incident light, electron escapes to the surrounding, right? Actually, this effect is observed by many scientists in the later part of 19th century and some or the other way. Like say a scientist observed it in this way. He was doing some experiment. There were two plates. One plate was at higher potential and other plate was at lower potential. When he threw some ultraviolet radiation on one plate, he observed that there was a current inside this tube, and you know the current is nothing but flow of charges, right? So there were some charges flowing inside this, and what happened when he switched off this UV radiation, that is when no light was falling on that, this current also stopped. So what does that mean? It means that some charged particles were emitted from this plate because of this ultraviolet radiation falling on that metal plate. This is something similar to what we have seen now, that is photoelectric effect. And since the charged particles were getting attracted towards the plate at higher potential, that is the positively charged plate, so you can say that the emitted particles are negatively charged particles, which we call as electrons now. Okay, the same experiment or the same phenomenon can be observed in a different way also. Like a scientist did this thing. He took a zinc plate which was initially charged with negative particles, that is initially it was having some negative charge. What he did, he threw some ultraviolet radiation again, and he saw that the plate lost its negative charge and became neutral because of this illumination of ultraviolet radiations. And if he threw again, that is if ultraviolet radiation was illuminated for a long time, he observed that the plate not only turned neutral but also it turned positive, which means some electrons were thrown out from this metal because of this illumination. And prolonged illumination leads to what? Even more electrons to escape, causes even more electrons to escape from this plate, and hence the plate is finally positively charged. Why these guys are using ultraviolet radiation only? Did you get that question? Because no electron emission was observed below certain frequency for each given metal actually, and that frequency is known as threshold frequency. and it depends on the metal. Say some metals like lithium, sodium, and potassium, cesium, they can give electrons easily, right? They were giving electrons with visible light also. But there were some other metals like say zinc, cadmium, or magnesium. These were not giving electrons with visible light, but they needed ultraviolet light, because the frequency of ultraviolet light is greater, and that's why these effects are seen. Now we shall do a proper experiment to observe all the effects of this photoelectric effect and carry out a detailed analysis ultraviolet rays of sufficient frequency or small enough wavelength, I should say, because if wavelength is less, frequency will be higher, right? So some ultraviolet radiation of sufficiently short wavelength is falling on this plate. So as usual, some negatively charged particles, that is electrons, are emitted, and because this plate is at higher potential, they move towards this plate. That is the experimental setup. And to control the potential difference between these two plates, we have a battery here, and the potential can be varied also using this one. So note that it is variable potential, and there is something called as a microammeter to measure the small currents in the circuit. Here, the intensity of the source, which is giving these rays, can also be controlled. That is simple, right? Bring this source near, you will get more intensity, and take this source away, you're going to get less intensity. That's it. Now let us see what are the observations. First observation, the intensity of light when it is increased, it was observed that the photoelectric current inside the tube was also increased, and that too it is linearly proportional, or you can say when the voltage and frequency are fixed, if you increase the intensity of light, more charges, that is current is nothing but rate of charge, right? So more charges were given out, that is more number of electrons were given out. So that's the first observation. Number of photoelectrons emitted per second is directly proportional to the intensity of radiation. Let's go forward. Let us see the effect of potential on photoelectric current. Observe this. First, when the photoelectric current was zero, there was some current. These are for three different intensities. First, let us concentrate on one intensity. Say I1. There was some current. When you increase the potential, what happens? Slowly there comes a state where the current is something like saturated. That is called as saturation current. And beyond that, whatever you increase the potential, however you increase the potential, nothing is going to take place, because what happens is electrons are emitted right from this plate. Not all the electrons will reach this plate. That's why current is not equal at all the time. But if you increase the potential for a reasonable amount, say this one, there what happens, all the emitted electrons are able to reach the plate. So that corresponds to the maximum current or saturation current for a given frequency, for a given intensity actually. And what else can happen? So beyond that, even if you increase your potential, current is not going to increase. Okay, this is fine. But what about this point? Till this one origin, this plate was at higher potential, right? So beyond that, what happens? If this plate is at lower potential, then that is going to oppose the motion of electrons, right? So electron is ejected, and it is again pushed back by this potential, the reversed potential. So what happens? Not all electrons can reach, only the electrons which have some kinetic energy, some decent amount of energy, can overcome the reverse effect and still can reach this plate. That's why you have some current here. And you increase the voltage in the reverse direction, that is, say this point, even less electrons can reach the other plate. So you have even less current. And similarly, when you increase the voltage in the other direction, say by V0, say there will be a value V0, which is called as cutoff voltage or retarding potential. Beyond this, at least at this point, current is zero, right? It means no electron which is emitted from this plate is able to reach the other plate. At this point, it means that the electron which is having the maximum kinetic energy of all the electrons emitted, even that is not able to reach the other plate when the potential difference is minus V0. So what does it mean? The kinetic energy of the maximum, or the maximum kinetic energy that an electron can have by this emission should be equal to E V naught, right? So this should be the maximum kinetic energy that an electron can have in this case. And this is how the kinetic energy of the electrons emitted is measured by cutoff voltage. And these three lines correspond to those of three different intensities. As you know, when you increase the intensity, current should increase, right? That's why for greater intensity, you have greater saturation current also. Hope everything is clear till now. And note that the cutoff voltage or the retarding potential is common for all the three intensities. Observe that. So it doesn't depend on the intensity. Actually, it depends on the frequency. Let us see how it depends. These are three different frequencies. V3, V2, V1 are related this way. The maximum frequency is V3, right? So you observe that the retarding potential is more for a greater frequency. So what does that mean? Retarding potential is what? It is a measure of the maximum kinetic energy that an electron can have, right? So it means that if you are using a light of greater frequency, your electrons have even more maximum kinetic energy. Are you getting me? So it is some frequency is actually related to the energy. So more the frequency, you can say that more energetic are the electrons. Actually, if you plot a graph between cutoff voltage, that is stopping potential, and frequency directly, for a given metal, it varies in this way. This beyond this, that is at this part, if frequency is low, electrons are not emitted first of all, that is threshold frequency. We discussed this before. And if the frequency is large enough, then the stopping potential varies in this way. Say for a metal A. For another metal B, it may be something like this. That means the nature will be same, just the threshold frequency will be different. So this is how cutoff voltage varies with frequency. So more the frequency, more is the cutoff voltage. Here also you observe the same thing. More the frequency, that is V3 greater, you need more cutoff voltage. If light is a wave, then what? Electrons that are present on the surface should absorb energy from the wave continuously, right? So if my frequency is small, okay, less energy will be absorbed, but it should take more time, right? If my frequency is less, so irrespective of my frequency, I should be able to pull out the electron with any frequency actually. Of course, if my frequency is less, it will take me more time, but still I should be able to pull out the electron, right? But that is not the case. Given the frequency is low, whatever time you illuminate the metal piece with light, you are not going to see any electron emission. So you can't explain that with wave theory of light. If that is possible, then the concept of concept of threshold frequency should not exist, right? But that's not the case. This is one drawback, and another is that light falls uniformly, right, on the entire metal piece. So all the electrons should get the energy, and so the energy distribution is very small, and each electron gains the energy at very small rate. So it should take very large time to eject one electron. So if you calculate it explicitly, you will find that one electron emission takes some hours or something like that. And it's not the case. Actually, photoelectric effect is observed within a fraction of second, something like 10 power minus 8, 10 power minus 9 seconds, in that order, if we see with wave picture. So since there are many number of electrons, energy absorbed per electron per unit time is very small, and hence it should take very large time. But actually, photoelectric effect is observed within a fraction of second, that is very small amount. So wave theory can't explain this also. And this led to a lot of chaos in the last part of 19th century. That is when our hero Albert Einstein came and gave a solution. And of course, he got Nobel Prize for that. Yes, Albert Einstein. Einstein was awarded Nobel Prize not for his famous theory of relativity. He was awarded Nobel Prize for solving photoelectric effect. Now, if you are getting introduced to these topics for the first time, I'm sure that you're curious enough to know how he solved this photoelectric effect, but I'm not left with enough time. So watch the next video. In that, I'll explain how he solved the photoelectric effect. It's going to be interesting. So keep watching. That's it for now. Bye.